Hi everyone. Today we're going to continue on our discussion on uh, parametric surface. Okay, so yesterday we get to talk about what happened when you define a vector value function of several variables, and also how to interpret what it does. And one way to interpret that is to interpret them as a transformation, which allow us to transform the domain into image, and the image must maintain the same dimension as the domain, but it could exist in a different dimension depending on how it map into what it map into. So as I say, one of the most basic example or one of the most basic way to use this type of functions is to form a function that map from R2 to R3 and therefore allow us to form a surface, a two-dimensional surface in R3. And because it's parametric, it allows us to actually form, give us great flexibility in forming different type of surfaces, where when we form a surface using an explicit function, we are not allowed to form a surface that kind of overlap itself. But using parametric representation to form a surface allow us to form a surface that have like multiple layer, and they can have a surface that go on top of each other. Meaning the following: if you use an explicit function like a function map from R2 to R1, I can only form like a hemisphere, a top half or the bottom half of a sphere. But using a parametric representation, I'll actually be able to form the entire sphere without actually any issues because of the fact that it's parametric. And we'll talk about how to generate a surface of a sphere later on. Okay, and we will get to that. But what I want to show you today would be this. What I want to show you is obviously derivatives. Shocking. I mean, we talk about each type of function and then we talk about the derivative of it. So, what we're going to be doing is called vector derivative. So now it's not new because you already know vector derivative back in 4.1, where we have a vector value single variable function. And so when you do that, you basically just differentiate each of the coordinate function. However, what we're going to be doing is a little different because we have multiple independent variables. So what happened is the following. So let's say we're going to let f be a function that maps from Rn to Rm. Okay, and we're going to define the following. So let's say the function f looks something like this. F of vector x is equal to f1 of vector x, f2 of vector x, dot 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 to fm of vector x. And what is vector x? Vector x actually consists of x1, x2, dot 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 to xn. So therefore, this function has n independent variables and m dependent variable. So this function, because they have m dependent variable, that would imply that each of its coordinate function, or it would have m that many coordinate function. And what happened to each of these coordinate function? Well, I'm going to call them f sub k. Each coordinate function would actually be a function that maps from Rn to R. Why is it from Rn to R? Because each of the coordinate function must require to take in the entire vector x to define. But since it only define one coordinate, therefore it must map into a real number, which represents whatever that coordinate is. Okay? And because of that, notice that these type of functions are exactly the same as the function that you learned in 4.2. And based on what we learned in 4.3, a function of several variable has what we call partial derivative. So f sub k has partial derivative. And therefore imply the following: if each coordinate function has partial derivative, then I can actually group all those partial derivative together and form what we call a vector partial derivative. Okay, so how do we define this? We're going to define the following. So if we collect all the partial derivatives of all the coordinate function together, as long as they're with the same independent variable, we can form something called a vector partial derivative. So how do we define this? So we're going to define vector partial derivative the following way. Okay. We'll define the vector partial derivative as follows. So we will define it kind of the same way we usually define it. We're going to have this notation, which is the scripted d, df over d vector x, d x sub k. So that would indicate the partial derivative with respect to x sub k. And what we do is to form this partial derivative, what I'm going to do is simply take the partial derivative of each coordinate function until I get all of them. Okay? And so this is called the vector partial derivative of the function f with respect to x sub k. Now it might seem like confusing, but it's actually pretty simple once you understand and basically the concept of partial derivative. Then you can simply just do them the same way. I'm going to show you what you have to do. So I'll give you a very simple example. Let's say we have this function right here. I'm going to let f of uv equal to u square v uv square. Notice this function. So note this function f mapped from R2 to R2. Therefore, it has two. You know what? It's okay. I'm going to do this. Two vector partial derivative. How do I know it has two vector partial derivative? Because that's indicated by the number of input that we have. We have two independent variables, therefore we have two partial derivative. Now, what happened to these vector partial derivatives? It's called vector partial derivative because they are vector. So the vector partial derivatives are vectors in R2. The reason why, because that is what the domain is. So therefore, we're basically finding two vectors in R2. One represents a partial derivative with respect to the first independent variable. The other second one represents the second independent variable. In this particular case, for this function f, the two independent variables are u and v. So therefore, the two vector partial derivative will be df over du and df over dv. So how do we actually find that? Well, actually pretty simple. Here, what we're going to do. Okay, oh, actually maybe I'll do it this way. So what is df over du? So that's basically meaning we take the derivative of the function f with respect to u. And so what is the function f? Well, the function f is actually a vectors in R2. And when I differentiate this vector, based on what we talk about, I simply just partially differentiate each of the coordinate function. So therefore it becomes this. So when I want to find a partial derivative of f with respect to u, I have to partially differentiate the function f with respect to u. Therefore, imply that I have to partially differentiate the vector that's represented by f with respect to u. And when I do that, I have to differentiate each of the coordinate function partially with respect to u. And now it's just basically two problems in one question, as what you have learned in 4.3. So when I differentiate u squared v with respect to u, we keep v as a constant and simply differentiate u. So u squared, the derivative would be 2u. So therefore this becomes 2uv. If I differentiate uv squared, then v squared is a constant, so that stays. And when I differentiate u, I get 1. So 1 times v squared is v squared. So that would be my df over du. And now I'm going to do that again for df over dv. So same logic, df over dv, meaning I'm differentiating partially the function f of uv with respect to v. And therefore, meaning that I have to differentiate the vector u squared v, uv squared. And when I differentiate this vector, I basically just differentiate each coordinates individually. And so when I do that, when I differentiate u squared v with respect to v, u squared is a constant, derivative of v is 1, so therefore it just becomes u squared times 1, which is u squared. And differentiate uv squared, u is a constant, derivative of v squared is 2v, so become 2uv. So this is what the partial derivative with respect to v look like. Now let's try another example, which this one maybe we can do it from R2 to R3. Or as a matter of fact, how about we do this one? I'm going to take f of uv, which equal to u cosine v, u sine vv. So that's my helix. And notice that this is a function f that met from R2 to R3. So what does that mean is that it has two vector partial derivative. And they are vectors in R3. Remember, I keep pointing out that you have to pay attention to things like this, like the dimension of the function, what's the dimension of the domain, what's the dimension of the range, because it all plays an important role in what you try to figure out. So that's the reason why you have to pay attention to it. And so now I'm ready to find the two partial derivatives. The two partial derivatives will be df over du and df over dv. And if you want to pause the video and just try to do it yourself and then check your answer, you should do so now before I continue. So what happened when I differentiate f with respect to u? Basically, I'm differentiating each of these with respect to u. Oops. And form a vector. And so if I'm doing this correctly, the derivative of u cosine v is a constant, the derivative of u is 1, so therefore it just becomes cosine v. And same thing happened here. Derivative of u is 1, and sine v is a constant, so therefore it becomes sine v times 1, which is sine v. And v is a constant. When differential with respect to u, I get 0. Now we can definitely do df over dv. So if you do that, you basically differentiate with respect to v of u cosine v, u sine v, v. So if I do that correctly, u is a constant, cosine v, the derivative is negative sine v, so it becomes negative u sine v. And this one should become u cosine v. And then derivative v with respect to v, this is a v, is just 1. So these two partial derivatives. Now that we have kind of ideas of how to figure out the vector partial derivative, what do they actually represent? So if you think about it, it should make sense the following way. So whenever we try to do a partial derivative, what we basically do is we try to keep all the variable fixed except one. So therefore, consider the following. Let's say given a function f that maps from Rn to Rm. If all the variables are fixed except one variable, then our function f that maps from Rn to Rm would simply turn into f that maps from R1 to Rm, with whatever the single variable that's not fixed. Now we know what kind of function this is. This is a curve. And that concept you actually have learned. Oh, excuse me. And that concept you actually have learned back in 4.2. And that concept is called coordinate curve. So therefore, this function right here will form a curve on the surface of f. And this curve is called a coordinate curve. A coordinate curve. And so what happened is, if I do have this coordinate curve, and now I'm going to take the derivative of this thing, which is essentially what our vector partial derivative is. So if we differentiate this curve, we form the vector partial derivative. Therefore implies that our vector partial derivative is the standard tangent vector for the coordinate curve. So that's important, is that the vector partial derivative are actually the standard tangent vector for the coordinate curve. Now, it might be hard to kind of see how that works, so maybe I'll show you a picture to kind of illustrate. Okay, so let's see if we can do that. Okay, suppose I have this function f that went from R2 to R3. And let's just first define what does this function do. Well, this function f basically represents a two-dimensional surface. So I'm going to just call that surface. Remember, when I say the word surface, it's basically referred to as a two-dimensional surface. It represents a surface in R3 in parametric representation. So let's look at a very basic function that we know. Let's say we have f of uv equal to u cosine v, u sine v, v. And I'm going to let my u go between 1 and 3. And I'm going to let my v go on to infinity. Okay? So now let's take a look at what this transformation would do. So what this transformation would do is it would take a two-dimensional a surface in R2 and turn it into some kind of surface in R3. And this is how this works. So here's my UV planes. Here's my 1, here's my 3. And since V go from 0 to infinity, maybe I'll do this. And then this surface just go on and on forever going up. Okay? So here's my domain. What does this function f do? Well, oops. So first of all, you have to realize is that it transforms it into R3 space. So let's see if I can draw this surface correctly. So here we go. So remember, this function actually formed the helix. So here's how I would imagine the function would look like. And then have a second one. So that would be how the surface would look like. Okay, it basically take this long, infinitely long rectangle and kind of bend it and have it spiral, have it rotate around the z-axis, and as it rotate around the z-axis, it rise up. Okay, kind of like a spiral staircase or like a slinky. Now here comes the interesting thing. So what happens if I fix one of the coordinates and let the other one just vary? So since this function have only two independent variables, so I can easily fix one of them by, let's say, having a specific u sub 0 value. So therefore, in this case, I'm basically have a fixed u sub 0 value, but the v can actually continue to change. So therefore, in the domain, it will be represented by this rate, u equal to u sub 0. It's not a line because it doesn't go on forever. So if you think about it, when I fix u to be u sub 0, what happened is my function f of x, f of uv would turn into f of u sub 0 v. And notice that means now I only have one variable that's changing, which is our v. That's why it become a curve. And how does this curve look like? In the image, it would probably look something like this. It would look something like a curve that kind of go around like this. So this is called a coordinate curve of v. And so therefore, if I now pick a specific point and try to form the derivative, let's say somewhere over here, Then the derivative would basically be called df over dv, which is basically the tangent vector of the coordinate curve at that one point. And you might also thinking that what happened to the other coordinate curve. Remember, because this function have two independent variables, therefore it should have two different type of coordinate curve, and you'll be correct. So the second type of coordinate curve will be like this one right here, which would be v equal to v sub 0. And if you think about this one right here, this will make f of uv turn into f of u v sub 0. So therefore, u is the only variable changing, while v sub 0 is now, while v is now fixed to be a v sub 0 value. And what would this coordinate curve look like on this picture? It will probably look something like this. I can probably draw it. Let's draw it right here. So that would be the coordinate curve of u, which just go across. And the tangent vector for this curve will probably go this way, because it's the straight line, and that would be df over du, or actually it might point inwards. I actually don't know which way it's going to point. Okay? So, unfortunately, I think I'm going to stop right here, and we'll finish up the rest of 4.4 in tomorrow's video. All right? Talk to you guys later. Bye-bye.